So before I pass it over to Michael and Simon, I did, since this is our last session of this year. I don't like saying last ever about anything, but definitely last of this year, 2024. I just wanted to share some stats about the actual program, the actual office hours program. So we started the vLLM office hours in May, and at the time, Michael had an idea to do office hours. He kind of got me to organize it. And my idea was to just do one or two of these, and just few minutes into the session, it was obvious that there was appetite to do more. So we ran a quick survey asking people how often should we do these, options being bi-weekly, monthly, or quarterly. And majority of the people said we want to do these bi-weekly, including my boss. So I was really kind of forced to do this. And as I said earlier and many times, this has become one of my favorite programs. So thank you so much for everybody that's enabled this to be a great place for the vLLM community to learn and engage with each other. So 16 sessions since the last, in the last 7.5 or so months. We've had 1,200 unique registrants representing at least 27 countries, and you can see the ones on the bottom right there that we've been able to track. But I'm sure there's many more. So if you are from a country that's now listed or whose flag is not on the bottom right corner of this slide, we'd love for you to just put that country in the chat right now so we can actually add your flag as we expand this audience further globally. We've had also, let me just mute a few people, sorry guys. We've had, all sorts of different companies join, from individuals to small startups to Fortune 500 companies, many of them that are listed right there. So it's really a vibrant community across all backgrounds and across the globe. We've had 700 unique attendees over the last 16 sessions. So thank you, everybody. There's few people here who have been to every single session. So thanks so much for supporting. 32,000 minutes attended, and we've answered about 264 questions in this forum. And we've had a discussion of it, many more. And, we've had 14 expert speakers join us, most of them being vLLM commuters. And we've received 25,000 views across YouTube and X. And it's been a really exciting journey. So thank you for all your support. Please continue joining us next year in every session, hopefully, and spread the word about office hours. If you know somebody who is, in love with vLLM as much as we are, this is a great program. We'd love to have you. So with that, Michael, I'm going to pass it to you. Why don't you just do a quick intro? There's a lot of new people here today.
Yeah. Hi, I'm Michael Goin. I'm an engineering lead at Neural Magic, committer on vLLM. Like Sal just said, it's been great to do office hours this year with you all, and hope to continue doing it great into next year. Yeah, so without further ado, we'll get into some new blogs. Actually, we released some at Neural Magic over the past 2 weeks. Definitely let us know if there's any blogs you want to highlight related to vLLM. But we've been working on these 2.4 sparse Llama 3.1 models for a while, and we just landed support for 2.4 sparse FP8 Llama on H100 GPUs or H200. And this is actually the first example of FP8 2.4 sparse kernels actually working in open source. Even NVIDIA Cutlass didn't have support for this until just recently. So we're really on the bleeding edge here, and we're really happy that the open source community now has the ability to do this. So we hope there'll be more 2.4 sparse models in the future, not just from our research team. So getting to a lot of the reasons while you're here first, we'll first get into a project update, what's new in the recently released 0.6.5. Some things to highlight are just, continuing progress on the V1 engine re-architecture, which, we should be announcing in an alpha capacity soon, along with Torch Compile, as we reported last time. Some particularly new things that I think are interesting are structured outputs now have a high performance implementation in vLLM that will be continuing to improve, but we've greatly removed some of the bad performance pitfalls with that I'll shortly go into. And then also with respect to prefix caching, an interesting optimization that you can find in the release notes is essentially making the scheduling aware of how much prefix caching we'll be able to get on given requests, which allows us to get much more efficiency when scheduling requests and realizing oh, we don't actually need to allocate, a bunch of blocks that we just end up hitting a cache for. And then, of course, what you're probably here for is to hear the retrospective of the past year and the 2025 roadmap from one of the main guys himself, Simon Moe, from UC Berkeley and maintainer on vLLM. And just as a reminder, we'll have 2 more talks already planned in January for the next month. I'll do a general project update and we'll lead an open discussion. And we'll do a deep dive into distributed inference with vLLM from Murali from SentiML, who worked on pipeline parallelism. And Nick Hill from Red Hat, who's been working on a lot of the distributed inference as well. And of course, the multi-process optimizations. So without further ado, if you aren't familiar with vLLM yet, just a quick introduction. It's the most easy to use, most popular open source inference server. It's really easy to get started. It has Python APIs for offline batched inference, hosting on multiple GPUs, and of course a really high performance server with OpenAI compatible APIs. So you can immediately get into self-hosting your own open source models on whatever kind of hardware you're working on. The reason why it's so popular is because it supports dozens and dozens of models from transformers, and it adopts the state-of-the-art inference acceleration research, like we'll get into, and of course supports many different hardware backends like NVIDIA, AMD, Google, AWS, Intel, and even CPUs. We have x86 here, but also ARM and PowerPC CPUs are even supported. And some of the inference features, we support like not just text decoder only models. We've been working a lot on encoders, encoder decoders, multimodal models, reward modeling, which will move vLLM to be used in more opportunities, actually, even than just inference, into post-training and RLHF, which we think is really interesting, and Simon will cover. And of course, quantization. We at Neural Magic have worked a lot on bringing activation quantization and particularly FP8 into vLLM. So we're really excited to keep growing the number of quantization methods. I think we're quickly getting to close to a dozen. And then, of course, all the system level optimizations and sort of algorithmic optimizations you would expect with state-of-the-art inference serving systems like chunk prefill, automatic prefix caching, batch LoRa inference, speculative decoding, disaggregated prefill. And then, of course, from an application level, being able to use tools or function calling with your models, having structured outputs, so you can get structured, parsable, outputs from your models to drive your applications. And then, of course, different levels of parallelism, tensor parallelism, pipeline parallelism, so you can deploy models across a variety of hardware accelerators and even nodes of accelerators for hosting really large models or really high throughput workloads. A quick quip about Neural Magic and who we are. We're a top contributor to vLLM. We've been spending obviously a lot of time on it this year, and it's been a pleasure hosting these office hours. How we work is we contribute a lot to the project, and we also produce enterprise-ready distributions of vLLM. So enterprises that have early success with vLLM, and they need expert support and kind of the boring software engineering things to bring that to scale. There are millions of users. We can help them bring vLLM to their AI inference infrastructure and scale it out. So quickly going into what's new in 0.6.5. There's a lot, spoiler alert. As I mentioned, there's been a lot of progress on V1 and particularly multimodal support in V1. We expect to see a lot of performance improvements for multimodal models in V1. So definitely stay tuned for that when we announce the alpha support. Also for Torch Compile, there's been a lot of work on sort of unifying all the attention backends so they can all be supported inside of Torch Compile. And of course, expanding the number of models that are supported, like encoder-based models, not just decoder only. We've also started introducing some of the custom passes and essentially operator fusions that we've been talking about for a while and justifying the use of Torch Compile for, such as fusing FP8 or int8 quantization onto previous operations, rather than needing to separately, quantize your activations and then read those activations into GEM, we can now, quantize the activations on the output of an RMS norm and save some reads and writes, and particularly improve latency. Of course, we're always expanding model support. The latest OMO model drop, and multimodal granite models, ARIA, cross encoders. Definitely dig into the list if you're interested. A big thing which we'll get into a bit more is we added X grammar as the default guided decoding backend. This offers some really large performance improvements. And then, as always, increased hardware enablement for AMD GPUs. We actually added support for, or sort of experimental support for ARM CPUs, a full CPU backend. So you can kind of run vLLM on your M1 MacBook or M series MacBooks now, and as well as expanding support for other backends like TPUs got prefix caching, XPUs got AWQ, GPTQ, weight-only quantization support, and various other stuff. One note that shouldn't really be a breaking change, but we did change the default temperature for chat completion requests in the OpenAI API from 0.7 to 1.0 in order to more closely match what OpenAI's default is. Yeah, that's basically kind of covered it from the highlights. So there's a little bit more just to cover, the prefix cache-aware scheduling. We also added support for proper sliding window support. So this means you can use like the full context length on Gemma 2 models. And particularly this was added to support the Ministral models from Mistral a bit better, as they use complex sort of stacked 4-layer overlapping sliding windows. As well as some sort of general optimizations for disaggregated prefill and prefix caching. We also added some new benchmarking scripts, a key one for structured outputs and vision data sets. Of course, the structured outputs one was crucial for us measuring our performance differences there. And as well as some user niceties and a lot of documentation. You'll see this sort of increasing. We hear you loud and clear. We want to improve the overall architecture and introduction details for new users coming to the project, so they can understand how to easily get started, how to easily start integrating, and especially we think some of the plugin systems will help users that want to make out of tree enhancements to the project can easily get more started and aren't sort of blocked on getting their features accepted into the main branch. Okay. And then, as I mentioned, I wanted to do a quick call out on the performance structured outputs. Spoiler alert, I did work on this, but also Aaron from BentoML, as well as a developer from Intel, Red Hat, a few developers from Red Hat. So it was sort of a lot of people working on this as a quick sprint to get the performance in a good place. If you're not familiar with structured outputs, it's essentially a general way to describe, when you want to make a request of a model and you need it to always have its request in a certain parsable format. So if you need to parse it, if you want the output of the model to be a parsable JSON object, either a general one or a very specific JSON schema, or you want it to map to some sort of, pydantic object, there's lots of different use cases for this. And it's a very useful thing that's used in a lot of applications on top of vLLMs. So vLLM has supported this feature and it's been functional for a long time. However, the performance has not been good. I have some sort of graphs on the right side showing time to first token as we scale up QPS on a sort of a JSON schema data set, where it's a log scale, and we're talking about tens, if not hundreds of seconds waiting on time to first token for requests, as well as below showing time per output token really getting quite bad in 0.6.4. But now, with the latest enhancements in 0.6.5, we really don't see, we kind of see acceptable and expected scaling as QPS. increases for time to first token and teapot as if we weren't even using structured outputs at all. So that's what we've achieved now. Now in the future, we'll be bringing and implementing structured outputs in V1 a bit differently, bringing it into the scheduler so we can start to do, structured output aware optimizations. Essentially, based on the grammar, we can know what the next, 8 tokens are in some cases, and so we don't even need to decode. Run all those tokens through the model in that case and decode them individually. We can just simply fetch those from the finite state machine we have from the grammar and do short prefills to essentially kind of speculate, obviously in a lossy way because we're doing structured outputs, but actually offer performance optimizations over vanilla decoding. So we hope this will be a useful feature and make inference cheaper for people using structured outputs.
Hi everybody, I'm Simon. I'm a PhD student at UC Berkeley. I help co-lead the vLLM project, and today I'll give you a quick sort of recap of the progress so far, as well as where do we see vLLM in 2025. So to start with, of course, we'll start with some metrics, and so one thing I would typically say is that star counts are not necessarily representative of the real usage, but it does show a lot of sort of the interest among the developers. So over 2024, we have seen sort of doubling of the stars as well as almost 4x of our contributor counts. And usage-wise, we'll dive into this later. We can see about a 10x GPU hours over the last 6 months. This is where sort of we started collecting some of the data. Download, of course, you can see on the right of the graph has also grown quite a lot. And concretely, we believe the reason for the growth is really the growth of the model supported, hardware supported, and feature sets supported. On the model coverage side, in January, we only see, like, if you use vLLM for January, it's really optimized for Llama and Mixtral. But as of now, we cover almost all the open source LLMs out there, as well as different kinds of modality, including image, video, and audio. And then we also support encoder-decoder model and embedding model to sort of cover the entire LLM inference spectrum. And then probably first among all the inference engine, we have support for state space models, and we're pretty excited about this. On the hardware coverage, in January, vLLM is really optimized for A100s, and we have experimental support for AMD. But looking at now, we are optimized for H100, A100, essentially the entire suite of NVIDIA's current generation offering, as well as in production in many cases for AMD, for Intel CPU, GPU, and Inferentia from AWS. And Gaudi has been in experimental stage and upstream to the repository, and people have been taking our TPU implementation for Spin. So we're pretty excited as we go forward that you will really have a lot of choices on the hardware to run LLM on. Community-wise, in January, the contribution community is really just from us from Berkeley, as well as engineers from Anyscale. But now, over the last 12 months, we have really seen growing full-time contribution, including amazing folks at Neuromagics and others to be directly involved, which we are very happy and fortunate about. Cool. All right, and so I'll move on to the next slide. So as I mentioned, we have added a lot of model, added a lot of hardware. On the feature side, we have really much a big wall of features. Each of these points represents like months and months of works by any individual or team. And a lot of those are indeed we're seeing as a part of the community. So we have added, just to highlight a few, pretty much the state-of-the-art quantization method and kernels, as well as Michael mentioned, structure output and distributed inference. These combined together are pretty much what powers like large scale deployments today. We also have features that enable you to better tune your workload for for long context scenarios or for different kinds of network topologies, such as chunk prefill and pipeline parallelism. And then really performance enhancement, where you will lower your latency and lower your sort of cost of inference, like features like automatic prefix caching and speculative decoding, as well as more sort of future-proofing features that will help us to bring more extensibility as well as more customizability, such as torch compile and disaggregated prefill to in our feature suite. So of course, these are very much only high level of what we have added over the last 12 months, and then looking forward to discuss more on this front later. All right, now, as I hinted before, we have this link, which is really just a report that we put together on the data we have so far, and really a snapshot of the growth and usage of vLLM over the last sort of 6 months, really. So we really only started collecting around April and May. And so just to preface this data is entirely anonymous, and oftentimes it is opt-out. And therefore, we see this capture, which is really just a sample set of how vLLM is being used in the wild today. And we want this data to be there to help us prioritize which feature to support, which hardware to support, which model to architecture to optimize for. We're going to have no other identifiable information. And this will help us to deprecate features. For example, when we're trying to figure out whether or not we want to deprecate beam search, this group of data really help us to understand how it is used in the wild. So that's why we really want to encourage you folks to turn it down if possible, and that will help us to prioritize. Of course, everything we learn will be public and shared. And so just for the TLDR of the report, you can go to the link and sort of play with the data and to hover around and see and sort of ask questions. We really see the compute, total amount compute, even for the software data, is about 80,000 GPUs running nonstop. This is pretty exciting, as like almost if you add up all the GPUs running vLLM today, it's probably one of the world's largest training cluster. Of course, it's all different kinds of inference chip at this moment, but we're really happy about the amount of compute being used. Usage, as I mentioned before, 10x growth over the last 6 months. For models, we really see a power law where Llama and Goin is some of the largest amount in our subset of the data. Of course, we believe people are really deploying vLLM in their private settings with proprietary models. And but in the open world, we do see like these two models leading. On the hardware side, we are actually seeing a well-represented diversity within NVIDIA line, where you have H100, A100, and other sort of tailored inference chips for the serving workload. And we're pretty happy to see sort of AMD trending, where as we added AMD support, that's kind of the lower right, the red bar on there. You see people start using AMD GPUs for with VM support, which we think will be one of the future where you have the optionality among different hardware vendors. Cool. All right, so moving on. So really at a high level, if we look back, the team sort of reflected on what we did well and what can we improve on in 2024, just at a fairly high level that we believe the feature that we have supported is the right set of feature for folks to really run inference efficiently and in production. For a community, we're very humbled by the passionate community that both contribute, and give feedback to the project. And for performance, we believe that we have been increasingly ramping up the performance of vLLM on NVIDIA GPUs and others to help ensure that you can always trust vLLM with the leading performance. For things we can improve on, we believe as the project scale, we're sort of looking at different kinds of technical design points and trying to make sure that when you add that big wall of features I was showing you, it shouldn't like complicate each other. It should be all work well together. So this is kind of one of the things that we're doing in 2025, ensuring that our new V1 architecture can help ensure different optimization can fit well together. So this is where the technical design is something we're focusing on, as well as marketing. So we believe vLLM, a lot of features in vLLM are actually under sort of appreciated or not that understood. So we want to do a better job. And this is also things we need help on, that if you find some feature that's exciting, feel free to write a blog about it, tweet it out, and tell the world about it. And we'll try to do a better job there as well. And then, of course, prioritization. We'll love to prioritize more emerging feature, because typically when we have released a quarterly roadmap, it's kind of a well-balanced list. So as we move on to 2025, we would like to send a message where we are clearly prioritizing some features and with some ordering so that you clearly understand which feature are we absolutely going to deliver. And yeah, okay. So and then I'll quickly go over 3 slides on the vLLM vision for 2025. And oh, sorry, there's a question about whether or not there's any statistic on data set, sequence length, model size, and rate of request. We do not collect those. We believe those are potentially identifiable. So we want to make sure we're respecting the privacy and ensuring that we're not collecting too much information about that. But of course, if there's any way we can find the right balance that's not collecting too much information, but still help us understand sort of the sequence length, the model size, that will be very, very useful from our point of view. Yeah. Cool. All right, so for the emerging models, yes, so sorry, for 2025 vision, we already have 3 points. This is where do we see vLLM in 2025? For the emerging, so one is to support the emerging model of 2025. And the second point is about really support production deployments. And 3 is kind of not a very standard terms, but we want to build it as open as possible. This means both technically for open architecture, but also as a community, we want to ensure there's like the true open source nature of the project. So for the first part, supporting emerging models, alternatively, you can think of, we want to support, I'll frame it as GPT-4 level intelligence in one GPU, and also support like very, very large model efficiently. So because we're seeing in the future as a case where you have small yet mighty model, as well as large, very, very large model like 405B and beyond coexisting as part of the production deployment workflow. So, and this is cases where we're moving beyond, we're seeing a trend where we're moving beyond just dense models such as Llama or simple MLE like Mixtral, where we see a world that will have different model architecture optimized for different kinds of KV cache. This includes different kinds of KV cache sort of management, like as simple as adding sliding window, adding alternate layers, adding different kind of attention mechanism, adding sparsity. So we want to be well used to support that. For mixture of experts, we want to ensure that vLLM is in a good place to optimize for different kinds of mixture of experts. For example, we're working on a project to help optimize the DeepSeek V2 MLE, where the expert allocation is very much different from what you see in Mixtral. And we want to make sure that vLLM is well supporting all that. For long context, of course, different kinds of context parallelism, and as well as pre-field disaggregation, which can help with that. And we want to make sure vLLM is well set up for that as you add more and more context. And this is kind of the system optimization side. On the sort of general inference systems, like sort of tuning side, we want to make sure vLLM is well set up for different kinds of vertical applications. I'm just listing a sample here. For example, for reasoning, we want to support the very much long context, but also different kinds of control over sampling strategy. For coding, this is like more or less low latency, and we want to make sure speculative decoding works out of the box for different kinds of scenario there. For agentic use cases, structure outputs, as well as more concurrency is definitely needed, as well as creative use cases where you have more again, more different sampling strategy, more control over the outputs, and will be very, very much needed. So this really comes down to we want to find your vertical use cases that you're building on top of vLLM and brainstorm with you how can we improve the core of vLLM for such use cases. And then lastly, we're also seeing vLLM being used actively in data curation and RHF use cases. So this means beyond serving, we want to make sure vLLM is well optimized for all the life cycle of sort of the LLM in the world. Cool. All right. So for the production deployment sides, I will frame this as right now we have seen folks deploying vLLM at a scale where you're either very, very large or very, very small. Very small as in maybe 1 or 2 node, or sometimes even just scaling down to 0. And we really want to help in 2025 to bridge that gap as the application built on top of vLLM matures. So we believe 2025 will be the year of productionization of scale deployments. This means we'll help to build an ecosystem and recipe for different kinds of routing strategies, global caching strategy, as well as scaling strategies, and as well as ensure the core, which is the vLLM that deployed on each GPU, to be high performance by default. This means we want to ensure different kinds of quantization are well supported and oftentimes encouraged to turn on by default. We want to support speculative decoding, where you can turn it on and then you'll give you always benefits on latency, as well as predicted and structured outputs. This should help for more production use cases where the outputs is needed in, for example, JSON form or some grammar form, so that you can actually use it in your top level application. And this is where we really see the cluster solution have increased in importance, and we want to add support, for example, for prefill disaggregation. And lastly, we also need your help to help find and tune vLLM in different kinds of workload for different kinds of models and different kinds of hardware. So, and we want to make sure that vLLM out of the box really works for that scenario in mind. And lastly, this is a little bit less technical, that we want to build vLLM continuously in this open space, right? In 2024, we have joined the Linux Foundation as an incubation project, renewing our commitment to open source. And in 2025, we want to really ensure that we continue to have a community of passionate users, adopters, and contributors, and make sure vLLM can be extended and modified by anyone. And this is probably a little bit different from typical open source project function. I really want to welcome forks and monetization on top of vLLM, in the sense that we believe it's kind of the last point here. Like when you're choosing vLLM, you are putting down some investment into vLLM, and we want to have a positive return of investment. And so technically, this translates to we'll ship a performant yet modular V1 architecture, which we'll hope to discuss in the future session here, and also use a Torch Compile as an extension point. So both V1 architecture and Torch Compile will help to bring in very modular components in the architecture so that researchers can test out new ideas, and then adopters can really prototype even with private use cases. You'll see a future where vLLM being used in private use cases with very modular extension points. And on the contribution side, we're kind of running the one-of-a-kind kind of engineering organization where it's spanning across many different companies passionate about this. And really no one is true, there's no one big leader where you contribute more than 50%. vLLM is really, as you see sort of on the lower right, the contribution is fairly diverse and scattered around. And we believe this is kind of the future of open source software, and we're trying to push that to make everybody well coordinated so we can deliver features. All right, so kind of to summarize, right? In 2024, we have seen great growth, both in terms of the stars, the contributor, and the usage amounts. We added many new models, hardware optimizations, and it's really from you are the vLLM user community, and we are really much doubling down on the way of open source. For 2025, we want to support the emerging models and vertical use cases. We want to help create an ecosystem for the cluster solution so that you can really take vLLM in production in many larger scenarios. And then we believe this kind of open architecture to both in terms of community, but also in terms of code is our key to growth and adoptions. And we need your help. We need your help on engineering, marketing, coordination, and so many pieces. And you can sort of join the vLLM developer Slack, slack.vlm.ai, where you can ask more questions, and then we can discuss more if in any cases you want to contribute. All right, I think that's sort of all the pieces from my side, and we can transition into a lot more questions.
Yeah, great work, Simon. I think there's definitely a lot of questions to cover. Maybe I can prioritize some. Yeah, well, one is like, is FP8 E5M2 or E4M3? Yeah, when we mentioned like FP8 for activation quantization, or really for the model inference, that in that way we're doing E4M3. This is because you want like a smaller range but greater precision around 0. But a key thing during model inference is we have like proper scales so that our range is being scaled to only represent the maximum range. For KV cache quantization, we actually do support choosing either E5M3 or sorry, E5M2 or E4M3. I should also say this means 4 exponent bits, 3 mantissa bits. So yeah, and then there we just do abs max, scales. So just looking at the
we have a live question if you're done, Michael, from Ford, if you want to speak up.
Yeah. Just first, want to say thank you all so much to the vLLM community, because what the community is able to achieve is pretty incredible. I was just hoping to ask about disaggregated prefill. I know that the last office hours was Quintai, and unfortunately I missed that, and there was some great discussion about that. But I just saw the PR from Mooncake, and I know Quintai also has his like LM Cache project that he's working on, and there's a few different sort of third-party things working on that, and different approaches to having a disaggregated KV cache. And it's something that I think about a lot in terms of not only larger production environments, but also increasing context length and things like that. So I'm just curious if the vLLM strategy is going to be continuing to focus on third-party integrations, or if there's going to be more direct effort on creating a vLLM approach to like a vLLM specific approach to disaggregated prefill.
Yeah, so this is a great question. So for those, just to step back a little bit, Quintai's like last session, I believe it has been recorded and it's on YouTube. So if you miss it, feel free to watch for everybody. And for disaggregated prefill, actually we merged the PR from Mooncake, and then we also released some documentation around it. So in the latest release out 2 days ago, you will already be able to test it out in this kind of 1P, 1D use case where you have exactly a pair of prefill and desag, sort of the prefill and decode worker. So it's just like a start. So where do we want vLLM to be in this case is, first, we see prefill disaggregation is very critical and important. And for bigger and bigger model where you want to control the decode latency, and then you want to flexibly manage the fleet for different kinds of SLA, right? So this typically is with prefill disaggregation, it's very easy to translate product requirements of time to first token, what's your requirement for time to first token, and what's your requirement for inter-token latency into allocation of different prefill decode workers. And this can, and the reason that this will help long context is that the prefill, then you can very much schedule the prefill according to the context, pack different contexts together, as well as potentially perform a context parallel operation on the prefill worker without interrupting the decode. So this is kind of where we see the importance of prefill disaggregation in probably moving forward. And as for exactly how we're going to do it, so there are a few pieces. The vLLM core pieces, that will definitely, we will make sure it is well supported. But the way I'm defining a vLLM core piece is the thing that takes one model, runs on one GPU or one node, basically one deployment, one replica of a model. So very well. And then for the prefill disaggregation, we're actually not planning yet to have some sort of official solution. We want to ensure that we have several open solutions that work with vLLM extremely well and have the sort of the best hooks ready for that.
Yeah, it kind of gets into like larger scheduling and like routing decisions. And I think we are a bit unsure of like how high the LM should go here. But you know, for the moment, want to go not too high. Yeah, one question that we keep getting is on supporting like more like older GPUs, like particularly like Pascal support. I know has like always been sort of a question. Yeah, you know, it's a trade-off. You know, we kind of set the limit at Volta and not going below due to, you know, kind of like developer load and CI load and you know, wheel size load as well. So, you know, we still think, well, I mean, we know the vast majority of our usage is on A100s, H100s, and Ampere and Hopper, you know, generations of GPUs as well. So, you know, more importantly, we don't want sort of the performance and maintainability of leading hardware platforms to be limited, you know, because we need sort of legacy support. You know, this is kind of the reason why also, you know, we can only support like one version of PyTorch at a time. And we try very hard to upgrade to the latest version of PyTorch, like as soon as it comes out, and use like the latest versions of CUDA as well. So, you know, we very much are, you know, encouraging and are happy to have like the open source forks where people add Pascal support. It's not that many lines of code. But yeah, leaving it up to like us to maintain it in upstream, I think we just have like a bit of, you know, concerns about that. But you know, if it's really difficult to build it outside of vLLM, you know, definitely let us know. It shouldn't be that difficult. It should be pretty easy to add it to the CMake and other environment variables. But yeah, I mean, I think I think we kind of want to stick by that one.
We have one more live question, one more raised hand. You can go ahead.
Hello, my name is Chonghyuk, and I'm a software engineer at vLLM's, South Korea-based startup specializing in AI chips. And I have a few questions regarding your roadmap for hardware backends. The first question is vLLM moving towards hardware plugin support? If so, have you thought about a timeline or a roadmap and intermediate milestones towards it?
Yeah. So recently there's a RFC opened on sort of our pluggable hardware backend. So what we want to see in 2025 is that we have an architecture where the mainstream vLLM on the main repo, official release supports sort of the hardware that are popular and publicly available. And then we also want a very easy extension point so that you can implement your own hardware backend for vLLM and test it against all the other features we support so that you can release it. And we're happy also to host such projects under the vLLM project umbrella. And so the user experience we're thinking of can be something that people pip install vLLM and also install another package like vLLM Rebellion. And then with that, we'll be able to enable vLLM to work in the specific hardware. And this is where we kind of want the sort of future of our cross hardware, cross platform support to be.
Yeah. And also, I understand that vLLM's plan is to rely on PyTorch to support multiple hardware backends. So if so, what do you expect from hardware backends in PyTorch supports? For instance, like is support for Torch compile sufficient or additional capabilities such as like eager mode or Torch distributed also required?
Yeah, this really depends on the level of support you want. And so in from what we're seeing, you need Torch compile support. You need potentially adding some custom kernels depending on like the hardware specific architecture to get around the limitation of Torch compile or like swap in custom modules. As well as if you need TP support, then we'll make sure to design the right interface to make that pluggable. And everything you mentioned here, I believe, is something necessary. To add more, like there are potentially, if you want to tweak the scheduling policy as well as memory management strategy, we want to also make sure to build the right interface for that.
Right. Thank you. Lastly, you mentioned about like custom kernels. So when modifying like model definitions to support hardware backends, what kind of changes are recommended? So like is adding new custom ops considered a valid approach, or would extending hardware specific attention backends be appropriate?
This is something that we actually don't have an kind of official answer for. And that's something that will really welcome discussion. We have explored approaches like for different hardware backend right now we support have different kinds of attention backends. So these are in the attention backend kind of abstraction. But frankly, we're just exploring different kinds of design here.
Thank you.
We have more hand raised.
Hey, this is Jinke from Cambridge, Mass. I had a question around like, is there any plan to support serving multiple models with the same vLLM engine for V1? And especially thinking of cases around like routing and ensembles, right?
Yeah, so this is a thing that we have been hearing a lot and still getting feedback on. Like, and then we're definitely not ruling this out yet. And we're just trying to balance whether or not this is the right way, like having a single vLLM instance to serve multiple models versus you have multiple vLLM instance multiplexing on the same GPU or same set of GPUs. Like which approach are easier to operate and what are the complexity added to vLLM itself. So currently this is not in scope for V1, but we do believe V1's clear modular architecture can enable something like this to happen. So yeah, maybe stay tuned and we can continue to discuss this maybe in like later Q1.
It's promising, thank you.
Yeah, I'm curious, Simon. I remember one thing from the Snowflake meetup, like, and what they shared was they sort of had abilities to like switch models that were being served on a vLLM instance in order to like reduce startup. I think that could be a kind of like interesting thing to work on, but like as a first step. Yeah.
Definitely. Yeah.
Aaron, yeah. Thanks for the X grammar support, obviously.
Yeah, I just have a quick questions with Simon's mentioning about RLHF support for vLLM. Just that, like, I'm just curious at which part that vLLM will play into part here, given that I guess like RLHF are pretty much like a, like user front, right? Like a front end. If you think of how OpenAI RLHF works, right? Like you kind of have like a UI work for that. So where would like vLLM play into that sense?
Yeah, so I guess like probably is mostly the terminology that I need to probably change this to. Maybe you can say post-training, maybe you can say alignment. Like this is really just about how people are practically using vLLM today in this kind of process to generate score, and basically generate score are like basically in the RL term like roll out and also calculating the reward for different kinds of algorithms such as PPO and DPO and more involved RHF process. Yeah.
Okay, I see. Thank you.
And I also see questions in Zoom chats ask about. Okay, yeah. The latest unanswered one is about. I noticed from Zhao Xing, I noticed leader worker set has been introduced recently. I'm curious, what is the roadmap for vLLM plus Kubernetes? And we're pretty excited about this. Like, I think we're actively working with the Kubernetes community, both in Kserve as Kube AI and others, to figure out the right approach and right way. And vLLM is designed to be containerized and work well in any Kubernetes environments. And then this is sort of one of the cluster solution I was mentioning to see whether or not different kinds of components in Kubernetes can work well and map together so that you can have a large scale deployment. Yeah.
Sorry, yeah, just typing a few more responses. Are there any live questions that people want to dig into? Okay.
Yeah, I had a question on the chat, but I can just ask it live. I think earlier you mentioned that the disaggregated prefill is something that could help with longer contexts. Could you elaborate a little bit on that? Like, how does that specifically help?
Yeah, sounds good. So I kind of addressed this before, but let me just frame it at a different way. That I think longer context, a disaggregated prefill help longer context in two ways. One is that it helps you manage your TTFT and intertoken latency better. When you have a long prefill ahead, you can schedule better without interrupting the decode, so that you can keep the decode under a certain sort of SLA threshold. And the second part is that because you can separately scale the prefill instance, when you have a mix of long context and sort of long request and short request, you can manage and route them better. And additionally, when you have this kind of separation, running context parallelism become a lot easier when you know the only task for these workers are to run prefill. Of course, these are just sort of early ideas that we're exploring with the community.
Cool, thank you.
Cool.
Okay.
Yeah. Last 2 minutes. There's this one more slides, Michael.
Yeah, for sure. Thanks. Yeah. So as always, we want to remind you to contribute to vLLM if you love it and want to see change happen. The easiest way is to just like comment and ping us on things you're interested in. That's the kind of easiest prioritization metric, is like if people care enough to message us and ask for it. That definitely helps prioritize the lots of things we're excited to work on. Of course, you can hunt for issues yourself and just ask, like if someone's taken it. We're happy to help, kind of get you started and guided on things if no one's able to work on it. And of course, build with vLLM in order to understand, what it means to you and what it needs to change in order to better serve your needs and understand, you know, the serving metrics of and workloads of large language models. As always, you know, give us feedback. Let us know anything you want us to change or improve into the new year, both with vLLM and with the office hours here. You know, we hope to do even more events and more in-person meetups and all sorts of things to, you know, make this project more transparent and open for you all. We'll be, you know, of course, meet us in the upcoming year. We're planning an East Coast meetup in Boston, Cambridge in March of next year, but also look forward to some of the other meetups that we'll be announcing before then. And of course, as always, we're hiring at Neural Magic. If you want to work on vLLM and get paid, we're you know, a decent place to do that. So without further ado, you know, thanks, Simon, so much for covering the recap. I hope you all enjoyed this year of vLLM a lot. And here's the next one. Yeah, happy holidays. And thanks a lot for joining us.
Thanks, everyone. Happy holidays.
Thank you.